All right. This whole thing was preparation for actually writing language bindings. Why would you want to do language bindings in the first place? I mean, all the interesting ones are provided already, right? Maybe not. You might want to do language bindings for existing optimized code, and you want to use it as a library. You might have some code in your community that does something fast that you want to use within your Python code. And maybe you do that already, for example, by calling it via popen and communicating with pipes, which can be rather messy and also look rather ugly. So Python bindings can lead to cleaner code. Python in general is often used as a glue language, right? I mean, we often combine different tools like NumPy. Scikit-learn actually provides or links into many different libraries. So we're going to actually work through a notebook later that goes through the process of building language bindings with different tools. Before you do the notebook, you'll have to actually run a little build script. That's partly because the notebooks cache libraries, and otherwise it won't see them. But that's for later when you actually get to the notebook. I'm going to introduce 4 different ways of doing language bindings. The first one is the foreign function interface. Some of you might ask, why isn't he introducing C types? Because I don't like them. That's pretty much the reason. If you are familiar with C types and know how to use them, they're a great way to get a quick function and to just call it from Python. It has the advantage of being a built-in. The foreign function interface is not built in, but it's easier and safer to use. So let's say we have a C function called, in this case, word frequency. That will be our example. Word frequency takes a file name and a word that we're looking for, and basically counts the words in the file. And it has been optimized. It is fast, and we want to use it. With CFI, we just import the package. We define the function actually just like it was in the header file on the previous slide. We take the same arguments. We then open the dynamically loadable library where this function is stored. It's stored in libtext stats. And then we can call it. ts.workFrequency b test text b u. Since the argument here are char stars, we actually have to use a byte type in Python 3. Is anybody still using Python 2? Boo! Unless you really have a package that doesn't work with Python 3, you should switch. Python 2 has been deprecated, and it really looks like it's going to happen. Almost all the packages that are still being actively developed are switching. And some even are starting to deprecate Python 2. So unfortunately, one of the nice things about Python 2, so there are reasons to use it, is that this does not become a problem. But anyway, in Python 3 it is. We have to use byte types. It doesn't automatically map to char star. But with the CFI, there's actually nothing we can do about it. Who's using Fortran? And you won't get a boo from me now. I'll be quiet with my boos. OK. Fortran, 2003, I think. Or maybe it was 11. Introduced ISO-C bindings. ISO-C bindings finally give us a well-defined standard way of telling Fortran what name conventions it should use. You might have noticed if you have tried to call Fortran functions from other languages that they often have an underscore at the end. With ISO-C binding, you can actually tell it either not to do that, or you can even give it an arbitrary name that you want to use for linking to this function. So if you are using a new enough version of Fortran, this is actually an interesting way to go. CYTHON. If you come from Python and want to wrap a library or a function that is written in C or C++ or Fortran, I think CYTHON is the nicest way of doing it. CYTHON generates C code. So everything that we can call from C, we can call within CYTHON. So Fortran code, C code, and it even has a C++ mode, so you can do proper C++ codes. Here we just define, so we do we include an external header. In this case, it's text stats.h, and we tell it which function we want to use from this header. In this case, it's int word frequency char star word. And then we can call it. And again, since we're using Python 3, we have to convert this into a byte type. Now, proper Python bindings should look Pythonic. And why people might argue that, especially for the file name, even open or file likes a byte type. This is not what I would usually try first. And I didn't. I ran into the error. So how can I make this prettier? And this is the second part of language bindings. You usually have to do some marshalling of data. You have to convert your data from your Python data type to whatever your C, Fortran, C++ function is expecting. And CYTHON is very good at that. First of all, because it knows lots of the Python data types. And second, it knows how these map to C++ and C. So we can do something like this. We can write a wrapper function, word frequency, that takes a file name and a word. The file name then I can encode in UTF-8. The word I can encode in UTF-8. These are actually byte types in Python 3 now. I can then define these file name C and word C are the corresponding C char star variables, basically pointers to these. And then I call my word frequency with these. But I don't care, because once I wrote this wrapper, I'm never going to see this again. What I can do now is actually call word frequency like this. This doesn't just work for strings and char. This also works for standard vector, for example. If you are using standard vector double, the default way CYTHON will handle it is actually as a NumPy array. We can wrap C++ too. I don't really do C. So here I have a small point3D class, just something really simple. It has a constructor, actually has two constructors, and a translate function in two versions, and it has some private variables. The basic import is pretty much the same as before. I do a cdef import from the header file, and here I do the point3d, double x, y, z, and these are the functions that I want to define. Now notice that I'm not defining everything. I'm actually not doing the entire header. I'm just doing the ones that I want to wrap. There are two types of classes in CYTHON, as you have learned. Here I'm going to use an extension type class. So it is customary to keep a pointer to the original class called this pointer, just like it's customary to pass self as the argument to a method of a class. There is an additional cinit function that is called when the underlying, or to initialize the underlying C++ code, and a corresponding deallocator, so that I can actually construct and clean up my class cleanly when it goes out of scope in Python. Once I have this, I can use the function like this. I can, whoops, I guess that's the only example that I have. I can create one, I can then translate it, print it, and there will be more for you to do in the notebook. If you come from the C++ side, how many of you do more C++ programming than Python? Okay. Then PYBIND 11 actually is a very interesting option. PYBIND 11 is a derivative of boost Python without boost and continued development. So it's much lighter. You don't have to download all of boost to use this. But the basic approach is similar. So let's take our text stats again. So I'm including this as an external C header, and I should now say PYBIND 11, you write C++ code. This is not Python code, this is actually a C++ code that you write. You compile it with the C++ compiler, and you load it later as a dynamically loadable library. So we're really leaving the realm of Python here. But it does make for very nice Python extensions. So you define a module, and this module, for example, can have a documentation, can have a decent doc string, like it should. I can define my functions. I just reference the actual function to call, and here I write a doc string for the function. If you wonder what this is, these are raw strings in C++. Raw strings in C++ are like our triple quotes in Python. So additional, or the new lines and the indentation and all of that is included in the string. So this then will be the doc string that I later see. The advantage here, again, is we can do arbitrary marshalling because we are living in the C++ space, and it provides APIs for the Python for the Python types. So I can create, for example, NumPy array in C++ here, and then pass it back to Python. We import text stats just like we would import any other Python module, just with import text stats. And yeah, we actually can call it without doing anything, just with the strings, because it knows how to deal with strings. Wrapping a class with PYBIND 11 is not much more complicated than wrapping a function. Except that now we do have to define a class. Here we give as template argument our original class name. And again, for those of you not familiar with C++, I apologize, but for those that are, this is a nice way to do this. The functions are defined as normal. Again, I can also declare my documentation here within. Now, if you are not using modern, yes?
And a class can, and C++ can inherit from one of these classes with this extension that we just read.
Can a C++ class inherit from one of these extensions? I don't know. A Python class can.
A Python class can inherit from one of these extensions?
Yes.
Okay.
C++, I haven't tried it that way around yet.
That was my answer.
Because it's easier to write in Python than in C++. Then I said I'd write a class there and then they...
Oh.
But anyway, forget.
Okay. Sorry, I don't know.
No, it's fine.
If you're not using modern Fortran code, which of course you should be using, but if you're not, then there's a great tool to wrap it quickly and actually get nice Python bindings. And with not modern Fortran code, I unfortunately mean anything, well, so Fortran 95 is actually, Fortran 90 works. Fortran 95, some of it works. Fortran 77 is well supported. And unfortunately, there's not much developing happening with F2PY. But when it works, it's actually great. Let's say we have a Fortran module here, my points module, and just wanted to show that you actually can do modules and contains and subroutines. That does work. Then all you need to do to wrap it is call this. Then you can import these points. This is the module name. So I imported from points F. I can initialize it with a single point in this case. I can set a point. I can translate it. And I think this is really cool. See this? See what this is doing? Here, I actually return a tuple and do the expansion from Fortran 90. Because, how does it do this? It's basically using the intents that were in the original code. You'll see it later in the notebook. To derive which variables should be input and which ones should be returned. And if you have multiple intent outs, it will actually return a tuple. And this has worked for years. I mean, PYBIND can do that too, and CYTHON can do that too. But F2PY has been around much longer, and for every other language that actually was much harder. So this looks fairly Pythonic, I think. But what do I do with Fortran 77? Fortran 77 didn't know anything about intents. But Fortran 77 does know something about comments. So what they did, they introduced an F2PY comment that they actually interpret. So F2PY will pass comments that start with F2PY and use these intents on the existing variables to determine which ones are input variables and which ones it should return. And it can actually create Python bindings that are just as good as the ones that it does for Fortran 90. I think that actually should cover most applications. We had some small changes to the writing extensions with Python in the F2PY. And in the notebooks folder, so you should re-pull your notebook, and I think we can stop recording.